So, uh, hello everyone, and okay, I'll have to start my so uh, hello everyone, and so today we'll be taking a lecture on we'll be continuing whatever we have done so far, and yesterday we were discussing something about practical energy sources, and we did in the end we did one question regarding practical energy sources. Today we'll be continuing a few more problems on practical energy sources. We'll be seeing what is KCL, we'll be seeing what is KVL, and in the end we'll try and finish off with what is nodal analysis, right? So these are the four topics that we aim to finish today. Okay. Uh, in in the previous lecture we did such question, and today we'll approach such question. Now, see, in this question, what we are provided with. See, the question reads, the VI characteristics of the figure A. This is the figure A where we have a source voltage, we have source resistance and a load resistance. Clearly, the value of load resistance is given and it is mentioned to be 10 ohms. Now, also we see a VI characteristic graph. This VI characteristic graph is a graph between the load voltage and the load current. Because it is a circuit in series, the load current is also equal to the source current, right? So here we see the graph between load voltage and load current, which is also equal to the source current, right? This I is also equal to Is. This is Is for you, right? Now we need to determine the current value of current I. This is something that is desired. Everything Vf is not provided, Rs is not provided. See, this is the value, the rest of the values are given. We need to exploit the values in this graph. Like this is the graph that we'll be exploiting to get the values of Is or I as desired, right? So in these questions, in questions like these, you don't have to, stress out a lot. It is a very simple question. You have to simply go step by step. If we go step by step, we won't have any problem, solving such questions. Now, if we, traverse in loop like this, all the voltage drops in this, you know, loop, can we write Vs minus I times Rs? Because Is is equals to I, so we can write I times Rs minus I times RL equals to 0. Can we do that? Right? So can we also write Vs is equals to I times Rs plus RL, right? Right? Now, if we see this graph, we are given with two intercept values, right? Now, tell me when would the current, this current in the circuit be 0? When would this current be 0 in a circuit? Okay, this current would be 0, which is given in this graph. This current would be 0 when there is no current flowing in the circuit. That is what it means. When the current is 0, there won't be any current flowing. So can I say in such a condition when there is no current flowing, can I say V is equals to Vs when I equals to 0? When I equals to 0, V equals to Vs. Now, what is the value of Vs? What is the value of V when I is 0? V equals to minus 20. So, minus 20 equals to Vs, right? So this is one value that we have achieved so far using this point, right? Now we need to utilize the another point. Now clearly see this. In this case, there is the voltage is 0. When would you understand the voltage to go to 0? When would the voltage across any element be 0? See, whenever there is no potential drop across any element, what would that suggest? It would suggest that the 2 points are at same potential difference, at same potential. And when would that be? When there would be that, when it is connected through a strong, a conducting wire. And what is a conducting wire? It is a short circuit, right? So can I say when RL equals to 0, only then V would be 0, right? When would V be 0? When RL equals to 0, only then V will be 0, because it is a short circuit. Only in such condition V can be 0. Now when RL equals to 0, V would be 0, and we again utilizing this equation, can I write Vs equals to I times Rs? Again we are using the second condition when V equals to 0, right? Now Vs we calculated to be minus 20 I times I here again would be, through graph we have I to be minus 2, from graph we have I to be minus 2 and Rs. So can I say the source resistance comes out to be 10 ohms, right? Right? So we initially we were not given Vs and Is. We've used the graph, the information provided through the graph, and now we know what is Is and Rs, right? Now can I now redraw this circuit to be something of this sort? This was given in the question itself, and this is something that we have calculated, right? This is minus 20. This is your source resistance, which we have calculated to be 10 ohms, and this is our load resistance, which was provided. Now again applying Kirchhoff's law, can I write minus 20 minus I times 10 minus I times 10 equals to 0. The net voltage drops across a loop would be 0, right? So can I write minus 20 equals to I times 10 plus 10, that would be 20, right? Again, so can I write I equals to minus 1 ampere? So this was what was asked in the question, right? So these are questions of sorts where we are approaching practical energy sources. The value depends on the source resistance. So these are practical voltage sources. Now we are given with the characteristics. All we need to do is approach step by step, solve one by one, use the value given in the graph, and then we can get our desired values. Am I clear? Okay. Let's take another question of similar type. See, the VI characteristics of figure A is plotted in figure B. Another similar, question where we'll be, using values from the graph. Okay. Determine the current I in RL if RL equals to 2 ohms, and also find RS. See, we need to understand what is the current I. Remember the direction of the current, which is already provided in the question as this way, right, and we are given with characteristics, right. Now RL is given in the question to be 2 ohm, right. Okay, is there anything more in the question information? No, there is no other information. We are asked what is RS, right. Now again going step by step, right. First, when I equals to 0, tell me what is when I equals to 0, when current in the circuit would be 0, would the terminal voltage, this V, equal to Vs? Because again we are talking about a open circuit. So when V equals to Vs, when would such condition be? When I equals to 0. When I equals to 0, V would be V equal to Vs. Now what is when is I equal to 0? Tell me. When I equals to 0, this is this point, right? So can I write at point 0 comma 10, I will be equal to 0. So can I write V equals to Vs equals to 10 volts, right? Now similarly, we'll see what is, we'll derive the value at the second point. Now again, it is a similar question, absolutely similar question. Now again we are given with when V equals to 0. When will V equal to 0? When there will be, when the load resistance reduces to be a short circuit. So when V equals to 0, when V equals to 0, RL would equal to 0. Yes. So when RL equals to 0, again apply KVL here in this loop. Very clearly what we can see. Now remember the direction of current given in the circuit. You have to be very clear about the direction of current. Can I write Vs minus I times Rs minus I times RL equals to 0. See, if I flows in this direction, can I say minus I would be flowing in this direction, and minus I is the direction of our loop. So if I say plus Vs, then it would be minus Is times Rs, and again minus Is times RL. So we are be very clear about the direction of current given in the question. This is the direction given provided to you in the question itself. This is where from using which the graph has been plotted. So you cannot change this direction. All we can do is take a negative magnitude of the same current, right? So can I write when RL equals to 0, this is 0. See, in this condition this would be 0, so this would cease to exist. So can I write Vs is equal to minus plus, and this will go to the other side again. So this would be minus again. So it would be minus times IRS. Should I write it again? Yeah, wait, I'll write it completely. See, when RL equals to 0, this would, we can write it as plus IS RS. This would be again, this is 0, so again no point, and this would be Vs times, Vs is equals to minus IS RS, and IS is again equal to I, so we can write minus I times RS, right? Right? So, from here we can get Vs upon Rs is equals to minus I, right? Now tell me, from this, we have already calculated the value of Vs to be 10 volts. So can I replace Vs to be 10, RS is still to be calculated, so RS let it be there. Now using graph, can I say what is the value of when V equals to 0, what is the value of I given? I is given to be minus 5. Again, be very clear. You're talking about only the current. You're not, you won't be considering this magnitude. Don't get confused. It's a very silly mistake in case you make it one. So you given the value as minus 5, right? So can I write RS is equals to 2 ohms? Now tell me what was asked in the question. See what was asked in the question. We are desiring the magnitude of current I, right? And we have calculated, for now, we have calculated, Vs and Is, Vs and Rs. So now it is using this equation. See, this is the equation that we'll be using. Using this equation, now that we know Vs, now that we know Is, RL was given in the question. Can I calculate I? See, we'll do it. I'm rewriting this equation for you so that you don't have to, turn the page. Plus I times Rs plus I times RL is equals to 0. Vs is calculated to be 10 volts and I is, we need to calculate the value of Rs is 2 ohms. Again, I is not known. RL is given to be 2 ohms again. See here, RL is equals to 2 ohms equals to 0. This would imply your current I is equals to 10 upon 2 plus 2, that would be 2.5 amperes. Okay, so these are these are certain kind of questions that you may face, you may find in your exams, and these are very easy questions. These are literally very easy questions and you don't have to worry about such questions. See, again I'm showing you for once. Just be very clear. You have to you have to approach the question step by step. It's a very basic question. All you need to do is exploit the you know uh, the values provided in the graph. You'll see the intercept values at one point when voltage equals to 0. Whenever the voltage equals to 0, you need to understand the load resistance has reduced to 0. And whenever the current reduces to 0, you need to understand the source voltage would equal to the terminal voltage. So this is how we need to approach such questions. It's a very simple question, and generally, I'm not saying it for sure. Generally, we don't find questions on practical voltage sources. Generally, you'll find questions. In case you master what is uh, nodal analysis or mesh analysis, electronics would be a very smooth sail for you. So this is something very basic. I generally don't see a lot of questions on this topic, but still, because for the sake of completing it, you need to know such questions. Okay, this was the in continuation to yesterday's topic. Moving on, we'll be having today we'll be starting afresh with current Kirchhoff's current law, Kirchhoff's voltage law, and we'll try and finish nodal analysis. Right. So in before knowing what is Kirchhoff's current law, we need to understand what is a simple node and what is a principal node. Principal, the spelling is wrong here. Okay, it is PLE. Anyway, so a simple node is an interconnection between only two branches. So a simple node would be an interconnection between only two branches. So something of this sort. Even this qualifies as a node. Wherever you see a change in potential, that point in itself would become a node. So an interconnection between only two branches would be a simple node. So this qualifies as a node. Wherever you see a change in potential, you will mark it as a node. So in this case, when there is an interconnection between only two branches, such a node would be a simple node. Okay. Now talking about what is a principal node. So an interconnection between more than two branches. So what would that be? So this qualifies as a principal node. So whenever you see an interconnection of branches in like more than two branches, that would be a principal node. Okay. Now by definition, what is Kirchhoff's current law? A lumped In a lumped electric circuit, as you can see it on the screen also, for any of its node at any time, the algebraic sum of currents leaving the node is equal to 0. It is a very simple definition. See, at any point of time, the net current at a node, this net summation of current at any point of time, net I, summation of current would always be 0, right? So this is what is Kirchhoff's current law. It is applicable to, as you can see, it is applicable to lumped electric circuit only. Why not distributed? Because it is applicable to lumped electric circuit only. Now you need to be very clear about this. Otherwise, only binding condition on KCL, the only binding condition on KCL is it should be a lumped electric circuit. Okay. Other than that, it could be linear, it can be non-linear, it can be active or passive. See, the application of KCL will also find, in case you've studied what is the you studied what is BJT and everything. You'll understand KCL also applies to BJT and everything. So it is also applicable to active or passive, bilateral or unilateral. So in any case, this would hold true. But but you need to be very clear. It should be a lumped electric circuit. It cannot be a distributed electric circuit. Only then KCL would apply. So it is independent of the nature of circuit, other than lumped. Otherwise, any case, it is valid. Okay. See, uh, if I say that KCL follows, in KCL, the sum of currents at any point on a node would be equal to 0, So what is current? See, current is current is charge per unit time, right? dq by dt is current. So can I say, if I say net current at any point of time at a node would be equal to 0, can I say the total charge entering would be equal to total charge leaving. Does that also mean, tell me, does that also mean that KCL ensures conservation of charge, right? So if the net currents are equal, the total charge entering would be equal to total charge leaving at any point of time. That would also suggest KCL ensures conservation of charge, right? In also now again, can I again, because what is charge? Charge is equals to n times number of electron, right? 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 So tell me, can I write number of electrons entering would also be equal to number of electrons leaving. So it is just, it is just another way of, defining KCL. At max, you can probably be asked in a 1 mark question or 2 mark question, or probably just, just for your knowledge, you need to understand that KCL holds law of conservation of charge, right? So the total electrons entering would be also equal to the total electrons leaving. Okay? Okay. Next, again, you will find this, very boring and, just, something that I'm defining. Unless you're solving questions, there's no fun, getting to these values. But I, and most of you probably would also be very, acquainted with such concepts. But still, because we are completing a course, we need to understand one step by step what is, and in short, what is KCL and KVL, right? So, what is KVL? Again, very clearly, KVL is defined in a loop, in a lumped electric circuit for any of its loop, again at any time. The algebraic sum of branch voltages around the loop is equal to 0. It is something of this sort. Vs, V1, V2 and V3, right? So can I say again, when you traverse from negative to positive, that there's always gain. This is basic sign convention that we know. So whenever you traverse from negative to positive, there's always gain. So we will write plus Vs. Now we'll write plus to minus whenever we are traversing. It is always, there's always a negative sign. You need to understand this sign convention very clearly. Be very clear about it. Whenever you're traversing from negative to positive, whenever you're traversing from negative to positive, it is all, the sign convention would always be positive. From negative to positive, positive. From positive to negative, negative. It is a basic sign convention. You need to understand, like, if you see technically, I'll tell you why are these sign convention as such. This is KVL, right? See, whenever you are traversing from negative potential to positive potential, you have to, provide, need to do extra work, you need to exert work to traverse from negative to positive, and hence the sign convention is taken to be positive. Whenever you are, whenever you traveling from positive to negative, then you are, going from higher potential to lower potential. Now again you are delivering, and in this case the sign convention would be 0. Oh, sorry, negative, right? So this is, this is how we define KVL. This is something that you will be very, acquainted with from like your elementary lectures in network. But in any case, we have to cover it. Okay. case in now you need to understand what is nodal analysis. We'll be beginning with nodal analysis, and I had to give you a brief idea of what is KCL and KVL. But what is nodal analysis? See, whenever you're approaching nodal analysis, you need to be very clear one thing about KCL, right? And the other thing that you need to be very clear about is Ohm's law. What is Ohm's law? So, in very basic layman language, can I write V is equals to IR? Again, this is not how Ohm's law is defined, but again, at constant temperature T. But in a layman language, can I write V is equals to IR? So if you are, well versed with KCL, if you are well versed with Ohm's law, you will not have any problem solving questions on nodal analysis. And believe me, nodal analysis is one of the easiest ways to approach questions in network theory. The only thing you need to be very clear about nodal analysis is to identify nodes. You have to visit each node. You have to be very clear with the steps. You cannot skip steps in nodal analysis, and it's a very easy approach to solve questions. Okay. Okay, so in nodal analysis, step number one, what would be the step number one? You will have to find the number of nodes. Now what were nodes? In the previous slides, what did we see? What did we see the definition to be node as? Anywhere where there was an interconnection between two branches or more than two branches, that would qualify as a node, right? So first thing that we need to do in a nodal analysis, what would that be? Find the number of nodes. Okay, so one, we need to find the number of nodes. Will traverse step by step and tell me how many nodes are there. Can this qualify as a node? Tell me. See, we see interconnection of 1, 2, 3 branches. This is a node, right? So this is one node. Okay. This and this are at the same potential, so we will not write any node here because this is a conductor. So these two will be at the same potential. So again, this is not a node. Now traverse from here. Do you see a node here? Tell me. See, this is at the same potential, right? So do you see a node here? Would this qualify as a node? 1 and 2, right? So this is another node. Let us mark it as 2. Again, traverse from here, there is a potential wherever you see a change in potential, you will mark it as a node. So this would be your node number 3. Again, travel from here to here. Do you see, you encounter a resistor on the path? Do you see a change in node, change in voltage? Yes. So this would again be your node. Mark it as 4. Again, travel, see there is a change, you encounter an element, there would be definite change in potential, mark it as a node. Where travel, this is the same point, right? Right? Same point. So this will not qualify as a node because there is no potential difference. And from here on we had already defined node number 1. So again, all you need to do is travel. In case you're new to solving questions on nodal analysis, you need to be okay. You need to travel. point by point. See, in case this is your first node, just travel point by point and you'll realize wherever you encounter any element which is supposed to cause a change in potential, you will mark that point as a node. Okay, so starting with the ground potential, you see three interconnection, you will mark it as a node. Move on, uh, you encounter resistance, it is bound to make a change in the potential, you will mark it as node 2, right? Now you'll again encounter another, you encounter another element, this is your voltage source, you'll mark it as 3, 4 and 5 and so on. Now by definition, we did see what is principal node and what is simple node. Again, I'm taking you back to that slide. Simple node would be only two branches, principal node would be more than two branches, right? So tell me in this figure, how many principal nodes are there? Principal would be more than two branches, right? So 1, node number 1, it is principal. There are more than two branches, right? Node number 4, tell me, right? Node number 4, this node. And see, if you see node number 5, these are all what? Principal nodes, right? Now, if you see node number 2, node number 3, these would be your simple nodes. It's a very simple approach. See, all we need to do is we need to write down node voltage with respect to the ground voltage, which is always equal to 0. We'll choose, there's no, bounding condition on which node to be chosen as a ground voltage, but normally where a lot of, points are meeting, more than 3 points, it is conventionally taken to be 0 because then the calculations, are a little bit easier. So every other potential is written with respect to the ground node, which we generally use by reference as the point where a lot of branches are meeting. So here 1, 2, 3, three branches are meeting and it is, at a same potential. So this would be your ground node. Okay. From and from here on, we will write node equations by KCL or Ohm's law. It is a very simple approach. In this case, we'll see what to do. Wait. Okay, is it visible? Okay. So in this case, tell me uh, at node 4, where are we going to apply? At node 4. Now, because of KCL, we know all the leaving currents. We will assume all the leaving currents to be 0, like sum of all the leaving currents to be 0. These are your leaving currents, right? Right? So tell me, can I say I, the current through resistance R2, plus the current through the inductor IL, plus the current through capacitor IC equals to 0? Can I say that? Right? Now we know the potential here. The potential here we haven't marked it to be, this that was the second step which you have skipped here. But you shouldn't do that. We will mark the potential here to be, say, um, let's say this to be, V1. Okay, this to be, say, let's say this to be V2, right? This would be V2. Let's say this to be again V3, right? Can we say that? Can we say that? Okay, so tell me what is the current through IR2? Can I say V1 minus V2 upon R2? Simple application of Ohm's law. Did I not tell you KCL nodal analysis is basic application of concepts of KCL and Ohm's law. So you know the potential difference between now the current is in this direction, so the potential difference would be V1 minus V2 and the resistance encountered is only R2. So can I write the current IR to be V1 minus V2 upon R2? See, you need to be clear, this direction is taken here, so it is a leaving current, so we need to subtract V1 from V2, from V1 to V2, because the direction of current is taken to be this direction. All the currents are leaving, right? Okay, now tell me about the inductor. What is the current through an inductor? Can I write current through an inductor like this? Is it not this? V is equals to L di by dt, right? Right? So what would be the current in this case? 1 by L times integration from integration over minus infinity to times t. Can I say, can I get the current from here? Right? Now tell me what is the current across a capacitor? Right? Right? So this is at node 4. Right? Now similarly, you will find an equal, representation. You will find an equal representation. Okay. At node 5. Tell me what would you do at node 5? At node 5, can I write the net currents would be IC. Again, mark all currents to be leaving. It is the basic, parameter. Mark all leaving currents. Okay. So all currents are assumed to be leaving, plus IR3 minus I times, again this is the current. This is given in this direction, but we are taking all leaving currents. So this would be minus I times T, right? Right? Equals to 0. Okay, so it would be C d times dt upon, again now we're at node 5. Now we are at node 5, so we will write again leaving currents is the key. So V3 minus V1, this time we're talking about leaving current from this node, so this would be V3 minus V1 plus V2, rather V3 upon R3 minus I times T is equals to 0. See, for now, just, listen to whatever I'm saying. Once once we will approach questions, things would get easier. So this is how, this, whatever we have discussed so far, all you need to understand is how to identify nodes, how to write currents. So all currents are assumed to be, you need to understand one sign convention. So for now, you need to stick to, just the step, and that would be, you need to understand that all the currents you will assume to be leaving the node. Even when they're entering, you will take a minus sign convention. But because this is where, you will make a lot of silly mistakes. So assume all currents to be leaving. That would, you need to understand, you don't need to keep changing according to conditions. That would be easier if you stick to the plan. Okay, so for now, just understand what is told so far. All you need to know is how to mark directions of current, and how to, mark potentials, and where would you find a node. Now, there can also be a question, why did I not mark this node to be VT? See, you need to understand this node VT is not with reference to the ground potential. Any voltage that is marked in accordance to the ground potential. See, this VT, you again find there is a change here, right? So this is not with respect to ground potential. This is with respect to the this value here. So the potential here. So these two are at a potential difference of VT. So I can write this, no doubt about it. I can write it is VT plus potential drop in R1. This is equal to V2, but it is not directly equal to VT. So this probably could be a doubt, but this is why I wrote V2 here and not direct VT here with respect to ground. Okay? Okay. This would be the last question for you today, and this is what the question is. This is, the basic question that we'll be approaching, and from this question you need to understand the very basic concept of nodal analysis. We'll be doing more questions tomorrow also, but consider this as, we'll go step by step, and you need to understand, very basic principle of nodal analysis from this point itself. Okay, so what is given? Point number one, whenever you're approaching a question, see what is given, see what is not given. You're not given with this potential, okay? You're not given with this current. All the resistances are marked. Also, additionally, you will see there is a value of current which is given in this node, okay? See, whenever you're given with this such questions, see what you can utilize and what you can, derive from such, questions. Now, tell me, what can you, understand through these questions? Okay, what is V2? Can you calculate V2? Tell me. Okay, we won't be calculating V2. We'll be going step by step. Let's, go step by step. Tell me, what are the nodes here? Two of them are marked, but still, tell me, can you mark this one to be a ground potential? Right? So when this is ground, this would be potential with respect to grounds, which is given to be V1. This is defined to be V2. This V2 would also be here because it is at the same potential because it is a conducting band. So again, this would be V2. If this is V2, this would also be V2, right? This will be V1 because there is a resistance, otherwise this would also have the V1. Now, this here is E, right? This here would be E because there is no other element barring this potential energy source that we see. So the potential here is E, right? So we are going to step by step. First, at point, at potential V2. This is, let us mark this one to be node 1, this one to be node 2. Let's focus on node 2. Tell me, can you calculate V2? See, you are given with you're given with uh, resistance, you're given with current through the resistor. Can I write V2 is equals to I times R? That would be 2 times 4 is equals to 8 volt. The current flows from higher potential to lower potential. So this would be at higher potential. So this should be 8 only then, in case you have doubt with the sign convention, only then I'm saying. Otherwise it's very, normal to understand that this would be 8 volts. Right? Right? Also, now understand. Uh, this is this is your 8 volts, right? If this is 8 volts, would this potential also be equal to 8, right? This potential would also be equal to 8 because this is 8, this is in parallel. So in parallel the voltages are same. So this would also be equal to 8. So in resistance R1, in resistance R is equals to R1. Can I say voltage across R1 is equal to 8 volts and the resistance R1 is equals to 1 ohm. So the current through resistance R1 would be equal to what? 8 amperes. Can I say it? This is higher potential, this is lower potential. The current flows from higher potential to lower potential. This would be what? 8 amperes, right? Right? Now tell me, this is 2 amperes, this is 8 amperes, basic principle of, Kirchhoff's current law. What would be the current here? The sum of all currents at this point should be 0. This is 2, this is 8, then this should be minus 10 only, then at point 2, at node 2, tell me, at node 2. At node 2, the current through 1 ohm resistor. This is the 1 ohm I'm talking about, okay? Plus 2 amperes plus 8 amperes should be equal to 0, or current through 1 ohm resistor would be equal to minus 10 amperes, right? So this was the direction here, like this, because we are considering all leaving currents. So in this case, in case I change the direction, what would be the value of current here? This would be 10 amperes. Am I clear? Am I clear? Okay, okay, right? See, whatever whatever is given in the question, you need to understand. If you go step by step, you will understand each and every point and you will not get confused. See, again, now at this point, come to this point, this potential here, the potential difference here is already known to be 8 volts. This is 10 amperes. Sorry, this is what I wrote ohms. It is not ohms, it is amperes. This is amperes. This is 10 amperes. This is 1 ohm resistance. This is 8 volts. Can I write, tell me, from here, this is V1. Can I write in this loop, in this loop, in this loop, tell me, can I write from negative to positive? Whenever we traverse, we are doing work, we are exerting work, so that the sign convention would be positive. Minus 10 times 1. Again, from positive to negative we are losing energy, so minus 8 is equals to 0. So the potential V1 now comes out to be what? 18 volts, right? So when V1 equals to 18 volts, can I write the current in 6 ohm resistance? The current in 6 ohm resistance is equals to 18 divided by 6 would be equal to what? would be equal to what? 3 amperes, right? See, again applying nodal analysis here, simple KCL application here. This is 3, this is 10. So this definitely should have been what? 13. See? And what was asked in the question? The question was asking what is the current I, which we have calculated to be 13 amperes. Very simple. We are going, at each point we are applying either KCL or KVL. These are basic application of KCL and KVL. It is nothing more. And at max, another thing that we are using is Ohm's law. And you will see in the rest of your electronics, uh, lectures also. At max, like maximum, if you have mastered what is KCL, KVL, and Ohm's law, you will have no problem you'll encounter no problem in electronics at all. In solving question, in solving numericals at least. See, again, we'll be utilizing KVL here. And that is why I took, I started KCL and KVL both at the same time, even when we were covering nodal analysis. Because you need to understand that no question can be done on its own. Like in general, you cannot completely do questions based on KCL without, having knowledge of KVL. So again, tell me, the potential, what did we calculate V1 to be? 18. So this is 18. This is 1 ohm resistor. 13 ampere current is flowing in this loop. Can I calculate E? Can I calculate E? What would be E in this loop? E is equals to what? Or rather, go let's go by KVL. So if you traverse from here to here, negative to potential, negative to positive, that would be positive E. In the direction of current, there is always a drop of potential. So what would we write? Minus, what is I here? 13 ampere, that is what we calculated. What was the resistance that is encountered by the current? 1 ohm. And what is the potential here? V1. Here again V1 at a higher potential to here. Now V1 is calculated to be 18 volts. What will we write? Minus 18 volt equals to 0. Can I write? Can I write E is equals to 13 plus 18 is equals to what? 31 volts. So this was a very simple question. All you need to do is go step by step. You need to understand what we were given. You were given with only 2 ampere current, and rest everything was resistance. You were desired to calculate E and I. Okay, so when you have current, you can calculate the potential. When you have potential, you need to understand in parallel there is always same potential. When there is same potential and you are given with resistance, you can calculate current in this branch. Again, current in this branch and this branch is given. You can using KCL, you can calculate the current in this branch. And when you have current in this branch, again apply KVL. Apply KVL, get to know the potential here, right? Get to know the potential here. And when you know the potential V1, you can calculate again the current in this branch. You know the current in this branch, you know the current in this branch. Apply KCL, you will know the current in this branch. When you know the current in this branch, apply KVL. When you apply KVL, you will know what is E. So it is a simple, step by step application of whatever you have read so far. It is not difficult. It is all you need to understand is it is, you have to go, you have to apply everything that you know, and it will be very smooth sail for you. You need to be very clear with your concepts, and that is all you need. Okay. So that's it for today. Tomorrow we'll be taking a few more questions on KCL, rather nodal analysis, and we'll try and begin with mesh analysis. Although I'm not very sure if we can do that. And tomorrow, let's see if we can start a few questions on, dependent sources as well. So let's see if we can do that. Okay. See you tomorrow.